Hey everyone, in this video we're talking about elimination. Now elimination is this kind of neat idea that's unique to systems. Um, Substitution, we've done that outside of systems of equations before. Elimination, we really haven't seen before. What we do is we take a system right here, and we say, hey, if I add my top equation to my bottom equation, I have minus x plus x. That goes away, and I'm left with 2y. And 4 plus 6 is 10. So I know that twice y plus y, 2y, is equal to 10, which means that y has to be equal to 5. And then I can take that 5 and plug it back into this and get 5 minus x is equal to 4, or 5 plus x is equal to 6. And either way, I know that x has to be 1. So my solution better be 1, 5. When I have something lined up like this, my y's and my x's both on the same side in nice columns, nice column equal sign like that. That's when I know that I can use elimination. And what we do is we add 4y plus y to get 5y, minus 3x plus 3x to get 0. And if these aren't 0, then I can't use elimination. In this case, 5y is equal to 10, so y is equal to 2. If y is 2, then 2 plus 3x is 6. 2 plus 3x equals 6. That means that 3x equals 4, and x is 4/3. Our solution is 4/3 2. And this is one of the reasons why system elimination is so nice. Oftentimes, when fractions are involved, elimination gets us the answer with the minimum amount of hassle. Let's take a look at this system right here. My y's are lined up in columns. So when I add y minus y, it gets me 0, y. And I'll have minus x, that's minus 2x, is equal to 4. I add the two equations together, and I'm left with minus 2x is equal to 4. Notice how there's no y term. That's elimination. X would be equal to negative 2 after a little division. And if y minus x is equal to negative 7, then y plus 2 is equal to negative 7. Y is equal to negative 9. Our answer is negative 2, negative 9. But there's something else that we could do here. I could take, say, this equation right here and multiply it all by a negative 1. That would give me the system y minus x equals negative 7, and then changing every single sign, y plus x equals negative 11. Now when I add this new changed system, I'll get 2y is equal to negative 18, or y is equal to negative 9, which is exactly what I got after substituting x. So I can change using multiplication to get a different variable to eliminate. I can change both sides of one of those equations using multiplication. That's key to the flexibility of elimination. This is called the multiplication principle. We take an equation, we multiply both sides by the same value. And this new equation is still equivalent to the old one. It's similar to changing the denominator of a fraction. If I use this principle, I can get a variety of systems ready for elimination. For example, if I have x plus 2y equals 3 and x minus 6y is equal to 3, I can multiply this top equation by 3. I'll have x times 3, that's 3x, 2y times 3, that's 6y, and 3 times 3 which is 9. And now take a look right here. These y's would eliminate. And if I added, we'd have, let's see here, change that to red. 4x is equal to 12, so x is equal to 3. The other thing that I could do is I could take and I could multiply this whole equation, that second equation, by a -1. Then we'd have the same top equation, x plus 2y equals 3, but a new bottom equation, minus x plus 6y is equal to -3. And now, when I add these, I'll get 0x 8y is equal to 0, so y is equal to 0. And my solution would be 3, 0. That seems odd. We better check. 3 plus 0 equals 3. Top equation checks out. 3 minus 0 equals 3. Bottom equation checks out. Yup, that's our solution. And remember, when we are talking about lines and solutions, if they're not the same line, they only cross in one point. So if we find this solution, it is the solution. Let's look at some more. For this system, 2y plus x equals 1, y plus x equals -3, I can get this x eliminated if I make it negative. I want a negative x right here. So I multiply this whole bottom equation by a -1, and that gets me minus y minus x equals 3. And now x will eliminate if I add them together. In this next one, 2y minus 3x equals -4, y plus 2x equals -2. It's a little bit trickier, but I can take 3 and multiply it by 2 to get 6, and 2 and multiply it by 3 to get 6. And since their signs are opposite, x will again eliminate. Notice how I took these two coefficients and I multiplied them by each other. What I want to do is I want to find the least common multiple of these coefficients. It's similar to working with fractions. Now, let's go back to stuff with no solution. This first equation right here is solved for y. So we're going to substitute it in, and we'll get 6x minus 3y equals 12. And when we substitute, that's 6x minus 3 times 2x minus 5 is equal to 12. Distribution gets 6x minus 6x plus 15 equals 12. That's 15 equals 12? That's a false statement if I ever saw one, because 15's not 12. This bears some investigation. I'm going to solve the second equation for y, get it into slope-intercept form. And when we do that by subtracting 6x from both sides and dividing by a -3, we get y is equal to 2x minus 4. So our lines were y is equal to 2x minus 5 and y is equal to 2x minus 4. Both these lines have slope 2. They're not going to cross, they're parallel. This system has no solution. It's independent and inconsistent. Let's do another example. 3y is equal to x minus 3. 3x minus 9y is equal to 9. We can take this top equation right here and add 3 to both sides to get x is equal to 3y plus 3. Then we'll substitute into the other equation. We always want to use both equations to get 3 times the quantity 3y plus 3 minus 9y is equal to 9. Distribution gets us 3 times 3, or 9y, plus 3 times 3, which is 9, minus 9y is equal to 9. Wait a minute, 9y minus 9y, they cancel. We're left with 9 equals 9. 9 equals 9, that's a true statement, but it's not very helpful. But if we get these two equations into slope-intercept form, we can see what's going on. So we'll take 3y equals x minus 3 and divide everything by 3, and we get x over 3 minus 1, or 1/3 x minus 1. For the other one, we're going to subtract 3x from both sides, so minus 9y is equal to 9 minus 3x. And when we divide by negative 9, we'll get y is equal to x over 3 minus 1. Hey, that's the same line. Here's both of those lines graphed, right? You can totally see that it's two lines. So they're really the same line, which means that this is a dependent system. But it's still consistent. For example, look over here. 3, 0. 3, 0 is a solution, and 0, negative 1. That's a solution as well. And if I go back to our system right here, we can check that. Let's see, so we had 3, 0. That's 0 is equal to 3 minus 3. 0 equals 0. Yep, that works. And then 9 minus 0 is equal to 9. 9 equals 9. Yep. 3, 0 works for both of these. It's a solution. And our other proposition was 0, negative 1. So let's see here. Negative 3 is equal to 0 minus 3. Yep, that works. And then negative 3, or 0, minus 9 times a negative 1 is equal to 9. 9 equals 9. Yep, works there too. So this is also a solution. If I've got two solutions, I've got infinite solutions. All my solutions are every single point on this line. All of them, any of them work. Collectively, these are called systems without unique solutions. If the result of solving the solution of a system is a false statement, then the lines described by the equation are parallel and do not cross. If the result of solving a system is a true statement, then both equations describe the same line. Statements like 12 equals 15 are false. Statements like 1 equals 1 or 0 equals 0 are true. And when we have this false statement and parallel lines, that's independent but inconsistent. And when we have something from a true statement that's dependent but consistent. Otherwise, when we have the situation where they just kind of cross once, that's independent and consistent. Here's another example. Y minus 4x equals negative 3. 2y minus 8x equals negative 5. I'm going to take that top equation right here, y minus 4x equals negative 3, and multiply it by a negative 2. I get negative 2y plus 8x equals 6. So negative 2y plus 8x equals 6. Add that to my bottom equation right here. It gets me, let's see here, the y's cancel out, the x's cancel out. I'm left with 0, but 6 plus a negative 5, so 6 minus 5 is 1. Huh. 0 equals 1. That's not true. These are parallel lines. That's it for this. For more of these, see the homework video. I'll see you then. Bye.